Hi everyone, it's Mr. Glover checking in. We're going to do our first video lesson today. Before we get started, I want to just say a couple of things. First of all, just hope that everybody's doing well at home. I know it's a difficult time, and if you're anything like me, you're probably getting a little bit stir crazy, but unfortunately what we can do is the best we can. So I hope everybody's doing well, and I look forward to connecting with you all later on today. The other thing I'll say is just about these videos. I'm going to try to keep them fairly short and sweet, just so that they don't take up too much time to watch. They're more manageable that way, and also so that when you are watching the videos, the bandwidth doesn't become an issue either. So I'll try to shoot for around 30 minutes, and we'll see how it goes. So having said that, last chapter was on financial math. This chapter is on something called combinatorics. And basically, it's about figuring out number of ways of doing something or number of possible outcomes. We'll do things like figuring out how many ways you could draw a hand with all hearts in a 5-card hand. So before we do any of that stuff, we first of all have to kind of go through the basics, and that's going to be on what's called the counting principles. So essentially what we're doing today is figuring out ways of counting objects that might not be convenient to count one at a time. So the first strategy we're going to talk about is called a tree diagram. It's a visual strategy, helps us brainstorm all possible outcomes. So it's literally a way of writing out all possible outcomes. So let's start with an example. Olio's Pizza sells 4 kinds of pizza in 3 different sizes. If we initially select one kind of pizza and then a size, how many different possibilities of pizza and size are there? So we'll do a tree diagram first, and then we'll do an outcome table. For the tree diagram, we're going to have to create tiers to this. So at the very top tier, it's going to be pizzas or pizza choices. The middle tier is going to have to be the kind of pizza, and I'm just going to write that over here, kind. And then the bottom tier will have to be the size of pizza. We could have done it the other way around. We could have done size first and then kind next. It doesn't really matter. So we start with our pizza choices at the top, and we draw a branch down to each kind of pizza. And there's going to be 4 kinds. There's going to be type 1, type 2, type 3, and type 4. So we can draw a branch to each of these outcomes. And then from each of these outcomes, we have to list all possible sizes. So there's a small, medium, a large for every single type of pizza. So there's going to be a small, a medium, and a large option for each of our types of pizza. And we've got to write each one out. So small, medium, large, small, medium, large, small, medium, large, and small, medium, large. So that's what our tree diagram looks like for this example. And the way that you read this is you read from the top down. So let's just say that we were going to have pizza type 1 in a small. You would read down to 1 and then down the branch to small. And technically, we can even highlight it. This becomes one of our options. That could be a different option than, for example, if we wanted type 3 in a large. So if you want to count the number of options, you just have to count how many outcomes at the bottom you have. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got 12 possible combinations. An outcome table is it's just a table where you've got one option on one axis and another option on the other axis, and you literally list all of them. So for example, for this question, we'll do size on this side. So we'll go small, medium, and large. And across the top, we'll do the types of pizza. So we'll go 1, 2, 3, and 4. Like so. Then we just list the options. So this will be a small type 1. call it S1. This will be a small type 2, call it S2, and we can fill this in as using the same strategy. So S3, S4, M1, M2, M3, M4, L1, L2, L3, and L4. And now the S, M, and L just mean small, medium, and large. And then 1, 2, 3, 4 tells me what type of pizza. If you count all these up, you'll get the same number. You'll get 12 combinations because there's the same pizzas. It's just a different representation. 12 combinations. Let's try another one. A room has 2 dimming lights in it. If each light has 4 different settings, how many ways are there to set both lights? So we've got 2 lights. So there's going to be 2 tiers to our tree. Each light has 4 settings. How many ways are there to set the lights? So instead of splitting it into settings, we're going to split it into lights. So at the very top, we'll have number of options. And maybe we'll move this over a little bit. From that, we need to go down to light number 1. So we'll write light 1 as our first space. There's 4 options for light 1. It doesn't matter what they are. You could give them a label. I'm just going to call them option 1, 2, 3, or 4. Maybe 4 is max power and 1 is min power. And so we draw our branches from the tree diagram, coming from the top down to each of our options for light 1. Then we have to do the same for light 2. This is where you want to give yourself lots of space, because for every single one of our options for light 1, we're going to have 4 options for light 2. So we could choose option 1 for light 1, and that leaves us 4 options for light 2. We could choose option 2 for light 1, which would again leave us 4 options for light 2. And we just continue doing this until we've exhausted all possible options. So this is what our tree diagram looks like. Again, if you want to read it from the top down. So let's say we read from up here down to 3, and then from 3 down to 2. That would mean light 1 was on setting 3, and light 2 was on setting 2. If we want to figure out the total number of options, which I believe is what this question is asking us, we have to count the number on the bottom: 4, 8, 12, 16 possible outcomes. All right. Sometimes, though, it is not convenient to draw a tree diagram for every problem. So let's say I asked you how many 3-digit numbers can you possibly make? I don't think you want to draw a tree diagram with hundreds of options. So there is another way to do this. These types of problems with many outcomes are going to be the ones where you don't want to use tree diagram, and you want to use what's called the fundamental counting principle. So to explain the fundamental counting principle, I'm going to explain it using the technical language, and then I'll try to make sense of it a little bit. So if one task can be performed in what's called A ways, and the second can be performed in B ways, then the 2 tasks can be performed in A times B number of ways. So let's say that you were trying to solve a problem, and the first task you were trying to do had 4 options. And the second task you were trying to do had 3 options, and you wanted to figure out how many ways could we perform both of those tasks. Well, this was 4, and I think I said 3. You would have 4 times 3, or 12 possible options. Now, something to be really careful about with this fundamental counting principle It only works in AND situations. Only works in AND situations. Not OR situations. And now that's gonna sound kind of confusing. But basically, if you were given a problem where both tasks are being completed, so you're completing task 1 and task 2, then you can use this principle. But if I ask you how many ways could you complete one task or the other task, then you can't use the fundamental counting principle. It's a finicky little difference, but it does make a difference. So let's try this out. How many 2-digit even whole numbers are there? So when you're using the fundamental counting principle, usually, well, you're going to need at least 2 options. So usually the way I start it is by just drawing either a line or a box for each of those options. I'm just going to draw a line, but you can draw a box if you want. And then you have to think about what each line represents. The first line is going to represent digit 1. The second line is going to represent digit 2. And then on the line, you write how many options you've got. So if you're counting even whole numbers, well, that's going to be things like 0, 2, 4, 6, 8. But it also includes things like 10, 12, 14, 16, 18. So we've got some restrictions here. Digit 1 can be any number. It can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 0 to 9 as our options for digit 1. Digit 2, however, only has evens because you can't have an even number that ends in an odd number. So like 11 is not an even number. So for digit 2, we only have options like 0, 2, 4, 6, and 8. And that kind of limits us a little bit. And actually, digit 1, let's change our restriction from 0 to 9. Let's call it 1 to 9, because technically we aren't going to write many numbers like 0, 8. It's just going to be 8. So for digit 1, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 options. For digit 2, we have 1, 2, 3, 4, 5 options. So if we want to figure out the total number, we just multiply, and that gives us 45 even 2-digit whole numbers. So we've broken this problem up into a 2-digit problem. We figured out our restrictions on each of the digits, and then we multiplied how many outcomes for each one. Seems like it's kind of confusing, but the math here isn't that bad. It's just setting up the problem. That's the long word. So let's try another one. PC license plate has the pattern LLLNNN, and I don't know if this is right. It's probably not. How many license plates are possible where L is a letter and N is a number? So we're going to need to write out a blank for each of our letters or numbers in our license plate. There's going to be 6. So we'll go 1, 2, 3, 4, 5, 6 as our options. We then have to do a little bit of thinking about how many letters are there in the alphabet. And if you count them up, there's 26 letters. And if you think about how many numbers you have, well, you could go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. So for numbers, you've got 10 options. So if we want to figure out how many license plates are possible, we just have to remember that the first 3 have to be letters and the last 3 have to be numbers. And we just write out how many options. There's 26 letters, so 26 for that first letter, 26 for the second letter, 26 for the third letter, and then for each number, there's 10 choices. If we multiply all those together, we get 17,576,000 possible, oops, one more zero, possible plates. And we just multiply these together. So we're not restricted to just using 2 outcomes like we would or with the fundamental counting principle. We can extend this to as many as possible. How many are possible if the letters and numbers cannot be repeated? So this question is really similar. There's still going to be your 6 blanks. But the difference here is that now we have to reduce our options every time we use a letter or a number. So we've got 26 options for that first letter, but now only 25 for the second, and then only 24 for the third. For our numbers, we'd have 10 for the first option, but then we're only going to have 9 for the second and 8 for the third. If we multiply all of those together, we only get 11,232,000 possible outcomes. So it's still a lot, but it's less. And when you can't repeat things, you're going to end up with less options because the numbers you're multiplying are going to be smaller numbers. Let's try another one of these. So Winners is hiring. The manager has selected 4 possible applicants for 2 different positions at the store. In how many ways can the manager fill the positions? Using the fundamental counting principle or using a tree diagram? So you'll see here that one option's a lot easier than the other. Let's start with the tree diagram. We'll start at the top, which I guess we could just call options. And then underneath this, we have to think about job number 1. And we've got 4 possible applicants. So there's 4 options for job number 1. There's 1, 2, 3, or 4. And we draw a branch from the top to each of these options. Now, then we have to go to job 2. If we hired someone for job 1, they can't do job 2. So from job 1, if person 1 was selected for job 1, we could pick person 2, person 3, or person 4 for the second job. If we pick person 2 for job 1, we'd only have options 1, 3, and 4 for job 2. If we pick person 3 for job 1, we'd have 1, 2, and 4 for job 2. And if we picked person 4 for job 1, we'd only have 1, 2, and 3 for job 2. So if we use the tree diagram, we end up with 3, 6, 9, 12 options. And now that wasn't too bad, but it is quite a bit of work writing all these out. If you can use the counting principle, it's going to save you some time. So with the counting principle, we had 2 positions. We had job 1, and we had job 2. Now, job 1 has 4 possible applicants. Job 2 only had 3 applicants because we picked 1 for job 1. Multiply those and you still get 12 options. So I don't know which of these you're going to prefer using, but fundamental counting principle is what I'll use if given the option. Tree diagrams are going to take a lot more work. Okay, let's try another one of these. Andrew is a terrible speller and frequently misspells his own name. If he uses all the right letters, how many different ways can he misspell his name? And that should be his. So we've got to first think about how many letters are in his name. He's got 6 letters in his name. And I picked this name on purpose because it doesn't have repeated letters. We will talk about what to do with repeated letters in another day. So we start out by writing out a blank for each of the letters of his name. 1, 2, 3, 4, 5, 6 letters. And then we just have to write down how many options are for each letter. He starts with 6 for his first letter. Could be any of them. Once he uses 1 up, he's only got 5 options for the second letter. Then 4 for the third letter, 3 for the fourth, 2 for the 5th. When he gets to that last letter, he's used them all up except for what's left, just 1. If we multiply all these together, Andrew could misspell his name in 720 different ways. And now, let's take the same problem, but let's change the scenario a little bit. He knows the first 2 letters are correct. How many ways can he spell his or misspell his name now? So letter 1, he knows. So there's only one option. It's the right letter. Letter 2, he also knows. Only one option. It's the right letter. But then the rest of these, he can mess up. So he has 4 options for letter 3, 3 options for letter 4, 2 for letter 5, and 1 for letter 6. If we multiply those up, he's only got 24 ways to misspell his name. So you got to do a little bit of critical thinking, and you've got to do a bit of planning before you actually start multiplying numbers together. All right, fundamental counting principle is only useful if both tasks are completed at once. If a problem doesn't involve both tasks happening, we may not be able to use it. If this is the case, we may need to consider each outcome as a set of options. This is what you have to do if you're given an OR scenario, and it's a little bit more work. Count the number of ways of drawing a single card and getting either a black face card or an ace. We have to recognize, first of all, that this one's not saying a black face card and an ace, but it's asking for OR. Then we have to do a Venn diagram for the set of black face cards and the set of aces. And we have to see if any of them any of them overlap. Black face cards over here and aces over here. So the black face cards, you could have 2 different suits. You could have spades, or you could have clubs. You could have a jack, a queen, or a king of either or any black card. And technically, I think your textbook doesn't consider aces to be face cards, so just keep that in mind. I've always thought of them as face cards, but if you treat them as face cards in your work, you're probably going to end up with an answer that doesn't match. For aces, we've got all 4 suits. We've got the ace of hearts, we've got the ace of diamonds, we have the ace of spades, we have the ace of clubs. So if we were to join these together, anything that exists in either of these sets counts as an option because we have a black face card or an ace. If there was something in the middle, in an intersection between these two, like for example, if there was a king on both sides, we can't double count that. But because there's nothing in the intersect, we can just add all these up. So in terms of set theory, this is called a union. The union of A and B. We'll call A the first set, B the second set. That's going to be the number of elements in A, which is 1, 2, 3, 4, 5, 6, plus the number of elements in B, which is 4. Technically, we would subtract the union, or subtract A intersect B, but there's nothing there, so that's not really part of this. This is going to equal 10 outcomes. All right, one more problem. Count the number of ways of drawing a single card and getting either a red card or a 10. So now this is another OR problem, so we can't use the fundamental counting principle. It would be nice, but we can't. So either a red card or a 10. We've got to do a Venn diagram for red cards and 10s. And I'm going to make sure they overlap this time. Let's try that again. I'm going to make sure they overlap this time. Oh man. Because if they don't overlap, that means there's no intersection. And I know that there's some red cards that also happen to be 10s. So for red cards, there's all diamonds, which technically would be ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king. And then same thing with hearts, all hearts. So there's going to be ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I guess we'll put the 10 over here too. And we need a 10 for this one. For the 10s, we've got all 4 of our 10s. We've got the 10 of diamonds. We've got the 10 of hearts. We have the 10 of spades. And we have the 10 of clubs. So when we go to do the set theory thing here, we have to take the union and we have to subtract the intersect. And that's the part that's going to make this different from the last question. So the number of options equals the intersect of A and B, or sorry, the union of A and B. And remember, the union is just all of the elements in both sets added up. And we're going to subtract the intersect of A and B. So basically, we're taking everything that's in both sets, like adding all the numbers, and then we're going to subtract which ones are repeated. So the union of A and B, there's 26 in the first set, plus 4 in the second set. So we can go 26 plus 4. Maybe we'll use brackets so we remember this is what the union was. And we subtract the intersect. And there's only 2 things. There's the 10 of hearts and the 10 of diamonds. So we have to subtract 2 for our intersect. This is going to equal 30 minus 2, or it's going to equal 28 options, or 28 ways to pick. So you've got to be cautious and read the question very carefully. If the question's saying how many ways could you pick a red card and a 10, well, then you would take 2 lines, figure out how many red cards, write the number in the first line, figure out how many 10s, write the number in the second line. But if it says or, then you have to use set theory, and it's a little bit more involved. And so that's pretty much it today. We talked a bit about some visual representations. There's the tree diagram, there's the outcome table. We then moved into some algebra. We used the fundamental counting principle. And then if we can't use the counting principle because it's an OR problem, we can use set theory to answer the question. So I've got some questions for you to try. These are based on your workbook. This will be your first assignment. So I'll end the notes here, and if you've got any questions while you're working through your assignment, feel free to ask when we do our first Zoom session. All right, take care.